Hello and welcome to this video. I'm Sai and I'll be talking about a data structure called Hashmap or hash table. You are probably already familiar with this data structure and aware that it helps us store key value pairs and allows retrieving data using a key. But perhaps you aren't fully clear on how it works and when best we use it. In this video, I'll help answer these questions by explaining what a hashmap data structure is, how it works, its uses, etc. So without any more delay, let's get started. Let's have a look at why we might need a hash map in the first place. For this, I'm going to use a hypothetical scenario as an example. Let's imagine we are building an online shopping application for a grocery store. We've been asked to implement a feature where our code is given a product name as input and is required to return its price. To keep things simple, we'll use whole numbers instead of fractions for the values of prices. Since our grocery store stocks various fruits, let's start out with a few products such as peaches, cherries, bananas, and so on. Each product has a price assigned to it. As time goes by, more products will be added to this list and some might even be removed. An important requirement is that accessing the price of a fruit should be very fast, even if the list of products grows big to say 100,000 items. To allow our program to retrieve the price of a fruit, we need to store the data in a structure to be able to access it easily. Let's see if a plain array-like structure will work. For this, we can store the pairs of name and price in an array. Here we can see that at index 0, we have stored the pair peaches and its price. At index 1, we have stored the pair cherries and its price, and so on. Now if I wanted to retrieve the price of grapes, I will need to start checking every element from the index 0 to confirm if the name is grapes, and if it is, then retrieve the price from this array element. What would happen if there were 100,000 elements in this array and the fruit I wanted the price of was at position 90,000. The code would need to check every element until it found the fruit I was looking for. Our code would turn out to be quite slow in this scenario. This is because an array is most useful for accessing a given element when we already know the index of the element. But in our example, we only know the name of the fruit and we'd like to find its price. Now naturally, we want to fix the issues with the time it will take to access elements in random locations in the array. What if we were to divide all the elements in the array in multiple buckets or cohorts like these? This would work provided we had a mechanism to assign a fruit to a bucket. That way, when we need to get its price, we can go straight to the specific bucket and only have to search within this bucket rather than the entire list of fruits. So in our example, we can have say 3 buckets to start with, and if we can always guarantee that a specific fruit or product will be stored in a specific bucket, we can restrict our search to that bucket and thus speed up access. So how do we assign a specific bucket to a specific fruit so that it can be found in that bucket later on? What if we could use the name of the fruit and convert it into a number? One naive way would be to use the length of the fruit name. It might work, but it will lead to lots of fruits with the same number of characters in the name in the same bucket, and the distribution might not be equal. Luckily, there is already a way to do this sort of conversion called hash code calculation, and most modern programming languages provide methods to calculate a hash code from a given input. For example, in Python, you can use the method hash, passing in the data you want to calculate the hash code of, or if you use Java, you can use objects.hashcode method. Now you might be wondering, what does a hash code look like? Here are some examples. Note that the hash value can also be negative. As you can see in the table, hash codes can be quite large, and we have only 3 buckets in our example. Our next challenge is to map this large number to an appropriate bucket number. For this, we will use the mathematical operator called modulo, also called mod. Essentially, modulo calculates the remainder when one number is divided by another. So all we need to do is ignore the negative sign and mod the hash code by the total number of buckets. And by doing so, we'll get the bucket number in which to place the fruit. Simple, isn't it? You might have also noticed that each bucket has more than one type of fruit. This is called collision and is normal given the number of items is much bigger than the number of buckets. Now that we have figured out which buckets to store a given fruit and its price in, it becomes very efficient to look up a specific fruit by accessing a specific bucket. This mechanism is the basis of the hash map or hash table data structure. If you are familiar with Java, it is called Hashmap, or dictionary in Python, which is based on hash table. It is very useful when we need to store and access data associated with a name or an ID of some sort. This ID is called the hashmap key, and the data that we want to retrieve is called hashmap value. A hash map is internally organized as a bunch of buckets. Each bucket contains a collection of key value pairs. When a new item is added into the hash map or hash table, we need to tell it what the key is and what value we'd like to insert against this key. In our example of fruits, the fruit name can be the key and therefore its price will be the value. So our data might look like so in the hash map. Now let's understand how data is inserted into a hash map with key as the fruit's name and value as its price. Let's start off with an empty hash map. As you can see, we had 3 buckets initially and all 3 are empty. When we ask the hash map to insert a key and value, it will calculate the hash code of the key and decide which bucket to insert the key value pair in. Here are the fruits, their prices, and the bucket number, which is the remainder when we divide the positive hash code of the key with the total number of buckets. First, let's insert the pair peaches and its price. As the modulo by 3 of its hash code is 2, we insert this key value pair in bucket number 2. Using the same logic, let's insert the pair cherries and its price. Next, we'll insert bananas and its price into bucket 0. The next fruit we'd like to save in our hash map is grapes and its price. But because its hash code's modulo is 0 and bucket 0 already has an item, it will be stored in a collection inside the bucket. Similarly, we'll insert mangoes and kiwis and their respective prices. Now that we have stored our data in the hash map like so, we can access the prices of fruits by using the fruit name as the key to the map. Let's try to retrieve the price of cherries. To do this, the hash map will internally calculate the hash code of the key, that is the fruit name, and find the bucket number. Then it needs to check if this key, that is the fruit name, is present in the bucket. If found, the hash map will return back the value, which is the fruit's price. If not present, it will indicate this by usually returning a null value. If the bucket contains multiple fruits, the hash map will search for the specific fruit key we are after and find it in the collection of fruits in this bucket. Once it has found the fruit in the bucket, it will get back to us with its price. The price of any fruit stored in Hashmap can thus be obtained. So how does updating data in the Hashmap work? Let's say the price of peaches went up from 23 to 25. To do an update, we need to simply reinsert the fruit name and its new price back into the Hashmap. Since the fruit name is the key, the Hashmap will find the correct bucket where this value needs to be saved, and it will override the old value. Let's talk about deleting data from a hash map. Let's say we'd like to stop selling cherries in our store and would like to delete this from our hash map too. To delete cherries from our hash map, we need to provide the key to the hash map delete function. In this case, the key is the name cherries. Using this key, the hash map will locate the bucket which stores the collection containing the data about cherries. To do this, the same operation of calculating the hash code and then doing a modulo with the total number of buckets is performed. Once the bucket is identified, the hash map will check the collection and locate the cherries. If present, it will simply remove the cherries from the collection. So far, so good. But how does the hash map cope with growing number of fruits being thrown into its buckets? Wouldn't we find ourselves back to square one, where the collection inside each bucket is just too large and searching slows down again? This is where hash maps can be designed to be clever. For example, Java hash map allows an initial number of bucket called capacity and another parameter called load factor when we initialize it. This defines the limit on how much data that can be stored in the hash map. When the data inside a hash map grows beyond this limit, the number of buckets will automatically increase and all the data will be redistributed in the buckets. To wrap things up, hash map is a very important data structure that every developer must be aware of. Since the hash map allows fast access to data using a key without needing to iterate through all the data, it is very useful in scenarios like the one we talked about where the name acted as the key. A hash map can also be used to maintain how frequently something happens, such as how many times a word appears in a paragraph, or keeping track of the most searched word in a word search-like application. If you have used the dictionary, you will remember that it is organized alphabetically. When you need to find the meaning of a word, you simply search the correct subsection using the first alphabet of the word. You might have come across Dropbox-like cloud storage solutions used to store files on the cloud. Since there could potentially be multiple copies of the same file, it would be very inefficient to store those copies on every upload. An optimal solution might be to store a single copy of the file in the cloud and use the file's hash value as the key into a hash map structure. When a user uploads the same file, we can compute the hash value of the file. We can then check if the hash map already contains this file hash. If it does, the user can be given a link to the existing file itself. I hope this gives you some idea how useful hash maps or hash tables are. Can you think of more use cases? Let me know in the comment section of this video, and thank you for watching.